Hello students, welcome once again to Sourav Sir's classes. So today we are going to continue again on the same topic, that is real analysis. Okay, and in the previous video we spoke about a few monotonically monotonically increasing increasing or decreasing type of things I had explained to you in the previous video. Just go back to the previous video and check what was there in the previous video. Today we are going to talk about something else. That the first thing that today we are going to talk about would be the squeeze principle. Squeeze principle. Suppose I let us take three sequences say AN, BN, CN. Okay, suppose I have taken these three sequences. Alright, now if there are two parts to this squeeze theorem. The first one is limit n tends to infinity AN is equal to limit n tends to infinity Bn, that is equal to some limit L. Okay, and the second one says that if for some positive integer k, AN is less than equal to CN, which is less than equal to Bn, okay, for all n greater than equal to k, then limit n tends to infinity Cn will be equal to also L. What it means that this Cn will also tend to the same limit, okay, if it is between the two sequences. If it's greater than AN but less than Bn. Okay, let's go on to another Cauchy's theorem. That will be Cauchy's first theorem on limits. Cauchy's first theorem on limits. So what does Cauchy say on his first theorem on limits? It says that if AN is a sequence, and converges to L, then the sequence XN, where XN is equal to A1 plus A2 plus A3 plus dot 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 right until AN, whole thing divided by N. Okay, this sequence also converges to L. Okay, or you can write in short limit n tends to infinity, a n is equal to L implies limit n tends to infinity, a1 plus a2 plus dot 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 right until an divided by n is equal to also n. So you can write this in this way. So this is Cauchy's first theorem on limits, and I got a perfect example for you to show you how it is happening. Okay, so please concentrate. Let's give you an example. It says proof limit n tends to infinity 1 by n, 1 plus 1 by 2 plus 1 by 3 plus so on, 1 by n is equal to 0. Okay, so from here first we write let an is equal to 1 by n, and let's find its limit. So limit n tends to infinity, an is equal to limit n tends to infinity 1 by n equals to 0, right? 1 by infinity is 0. Again let xn is equal to 1 plus 1 by 2 plus 1 by 3 plus so on, 1 by n. Okay, now if you notice, now limit n tends to infinity, an into xn, so which is equal to limit n tends to infinity, an is 1 by n. Okay, 1 plus 1 by 2 plus 1 by 3 plus dot 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 1 by n. So this part is 0. You multiply this with this, it's a 0. So answer is 0. Okay, so very simply we have proved this. Okay, so you can see even this part, even for this part, even for this part you can also do this. Limit n tends to infinity, a1 plus a2 plus a3 plus dot 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 an divided by n is equal to 0. Okay, you can also write this. Alright, because a1 will be 1 by 1, a2 will be 2 by 2. Okay, a2 will be 1 by 2, because an is given as 1 by n, right? So if you have a1, then you have 1 by 1. If you have a2, then you have 1 by 2. If you have a3, then you have 1 by 3. Okay, like that one. Now let's go on to the next part, and that will be the opposite, that actually you should just keep it as a note. Okay, keep this as a note. It may happen that if limit n tends to infinity, a1 plus a2 plus a3 plus dot 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 right until an divided by n is equal to some limit L, but limit n tends to infinity, an may not be L. Okay, just the opposite of whatever I had written on top. In the first part I had said that if this an tends to L, then this has to tend to L also. But the opposite says that if this is tending to L, that not necessary that this will tend to the same thing, the same limit. Okay, so let's try and understand that. I got a perfect another example for you. for this one also, this note. So look at this. Suppose I take an to be minus 1 to the power n and xn to be same thing, a1 plus a2 plus a3 plus dot 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 right on till an divided by n, right? So let's see this limit. If you do limit n tends to infinity xn, you will get limit n tends to infinity, okay, a1 a2 a3 right on till an, divide by n. Of course, divide anything by infinity, it's 0. Okay, so see, limit n tends to infinity, xn is 0. Okay, but look at this, but limit of n tends to infinity an, okay, limit of n tends to infinity an is not convergent. So basically what we are trying to prove is, we are trying to prove that the top one, the top part, that is this part, actually not n tends to infinity, it will be not n tends to infinity, just hold on, I was writing limit n tends to infinity n, and I am writing that also here. So basically the an should not converge, okay, limit n tends to infinity may not be convergent. Okay, so you will notice that although this part is tending to 0, this part is tending to 0, this part, but this an is not convergent, an is not convergent, right? You can easily see from on top, check it out, an is not convergent, this will not converge, this will not converge, this will. So I have, okay students, so this was basically Cauchy's another theorem. Alright, so now we will talk about Cauchy's second theorem. Let us talk about Cauchy's second theorem from here. Okay, so look very carefully. It says, this is Cauchy's second theorem. Let's scroll down more. Cauchy's second theorem. What does Cauchy's second theorem say? It says that if an is a sequence, if an is a sequence of positive terms, then limit n tends to infinity an to the power 1 by n is equal to limit n tends to infinity n plus 1 divided by an. Okay, provided that the limit does exist at the right hand side. If the limit does not exist, then there is no use of doing this. Okay, so provided limit exists. Alright, so let's go ahead and see what we have learned for today. Alright, today we have learned how the squeeze theorem works, or the squeeze principle works. Okay, how the squeeze principle works, how when you have a function between you have a sequence that is between the two other sequences, okay, and if both the sequences on the outer end are tending to L, some limit L, okay, then definitely the sequence that is in the middle, that is Cn, okay, here Cn will also tend to L, okay. Next, Cauchy's first theorem on limits. What does Cauchy say on limits? That if there is a sequence and it converges to L, then xn, when it is given in this way, okay, will also converge to that L, okay, and this is the short form. This is the short form of what you will be writing on that, okay. Now the converse, the opposite of this, there is a proof. I have also proved it, so please check the proof, okay. So there is an also opposite of that. It says that if this is converging to L, if this whole summation is converging to L, not necessary that an will also converge to L, okay, or converge to anything, okay. It can converge but not to that. So you can see this is not a convergent sequence while this is converging to 0, okay. Very easily done, very nicely and easily done for you, okay. So that's it, students, for this video. Keep taking enough help, because all the help you need will be provided at Sourav Sir's classes. Thank you very much.